Okay. So for example, what the way ChatGPT is trained is that is what we call self-supervised learning, right? So we look at a sentence and we force the model to learn how to predict, some part of the same sentence by blanking, certain words, or by just giving a model some piece of text and making the next word that appears in that, sequence as the word that the model is going to predict. Um, okay. And what these models are, they are trained first on, using self-supervised learning on internet scale data and then fine-tuned for downstream applications. So one example that I'll show today would involve a pre-trained model, which is the vision transformer by Google, and fine-tuned later on a different data set, which is C500. So just to give you some numbers, the data set that is used by ChatGPT based models are very large. So GPT-3 is 17 gigabytes, GPT-4 45 gigabytes, and the model parameters are, the scale of billions to trillions of parameters. And I also give, training time. So if I have only one GPU, then there are certain estimates on the web that GPT-4 would take 6,000 years to train. And what is the amount of energy that GPT-4 requires in order for training? It's like driving a car for 18 million miles. But of course, that we don't want to train these models on one GPU, right? Because then it'll take forever. So we divide the computation and training on several machines and use distributed training methods and distributed computation architectures to solve the underlying giant machine learning problem, right? And this talk is on will be on design analysis of such training methods. And this is a very small piece of the huge giant puzzle, which, GPT type models are. Okay, so just a simple case study. So this is from a few years ago. So we train a model. This is a simple binary classification model where we do airplanes versus automobiles. And I have 10,000 images, 5,000 for airplanes, 5,000 for automobiles, given to a central machine to do binary classification. And if we look at the generalization accuracy, then we see that the center, which has all the data and does all the computation, does this processing, achieves 70% accuracy in 113 seconds. And if I were to take these 10,000 data points, divide it into 4 nodes of 4 computers, and do distributed training, so each computer does a small part of the training problem, then interacts with each other, then the same accuracy can be reached in something around 49 seconds, right? So we have the time that it takes to train this model, and without losing accuracy. There is a catch here, though, that what these local models or these distributed models do is that so each computer trains and then communicates with nearby computers or nodes to exchange information, and that communication adds latency. So I haven't included that latency in this picture. So if it takes 49 seconds to reach this accuracy, there is plus some communication delay. But communication, depending upon what modality you're using, is practically very fast. And in the context of data centers, they are very, very fast as well. So the goal of my talk would be that if we observe relationships like these, can we quantify them? Can we make them mathematically more precise? What does it mean to go from 113 seconds to 49 seconds, etc.? Okay. So I'll use a very simple, benign setup to explain my problem. So this is a simple binary classification, image classification setup. We have 2 different types of images that we want to distinguish. We want to learn a classifier that can distinguish between these 2 images. So my image is a vector in this high dimensional space theta j, and these are labeled images. So I know that whether this image was a stop sign or a yield sign. And I want to train a classifier, which is this straight line on this, or a hyperplane, this high dimensional vector space that can separate the classes of 2 images, right? So if you look at the red classifier, then I misclassified 3 red triangles and 3 red stars. So the score of this classifier, let's say, is 6. Versus if I look at the green classifier, then it misclassifies an additional green triangle. So the score of this green classifier is 7. So across all such straight lines in this R2, I want to pick the classifier that has the minimum score and that will be my decision boundary, for example. So if any new image comes in, I'll just see where it lies with respect to this straight line, and I'll declare it as a stop sign or a yield sign. So mathematically, I have my image theta j. I have my classifier x. Based upon that, I will predict a label to image j, and this yj hat is the machine. So it could be a simple binary classification logistic regression model, or it could be a very advanced, vision transformer with 70 million parameters. So the nonlinearity kind of comes, and the model architecture comes in this yj hat. X are the model parameters or the neural network weights. So in this simple case, X just defines the hyperplane. I compare it with the true label Y, right? And the comparison is evaluated with respect to a loss function. So this could be a squared error loss function. This could be logistic loss. This could be a 0-1 loss, your favorite loss. And I want to find the model weights X that minimize this particular loss, right? Okay. And in the distributed setup, what I will do is I will divide my training data set into multiple machines. So my training data indexes over machines and the sample j per machine, right? And otherwise, it's the same problem. And then I sum over the machines, sum of the data points at each machine and then sum over machines, right? So we know from our background, signal processing control, etc., that different loss functions will lead to different minimization problems. So for example, if in a simple, signal plus noise type of model, if your y hat is a linear predictor of the underlying parameter that you want to learn, and the loss function is quadratic, then what we are dealing with is a quadratic optimization problem. In case of logistic regression, etc., we have convex optimization problems. And when there are nonlinearities involved in your prediction or in your loss function, then we have a non-convex optimization problem. And if I want to solve a distributed minimization problem, which is training certain machine learning models, then different loss functions, different neural network architectures will give me different type of loss functions. And then we add certain other features of current machine learning kind of training methods. So for example, batch sizes, full gradient methods versus mini batch versus single measurement methods. Gradients are also imperfect. So for example, you don't get to see the full gradient of this loss function with respect to data, but up to a certain error. And these gradients can also be revealed to us in a streaming way, right? And if I want to add more of an autonomous agent flavor to it, then the nodes are mobile. So they are robots that are moving inside a confined space. So the network that I talked about earlier, where nodes are communicating, exchanging information about their learned parameter with other nodes, that network is stochastic now. So because we cannot guarantee at which time which node can see which other nodes, etc. So our focus is going to be on stochastic first order methods over variance function classes. So by first order, I mean that we are only allowed to look at the loss function through its gradients. Stochastic means that these loss functions or the gradients are not perfect. And stochastic also encapsulates the fact that the network over which these nodes communicate is not going to be perfect. And then the training data is distributed over a network of nodes, machines, devices, or robots. Any questions so far? Okay, good. So I'm gonna briefly define the functions that we want to minimize. So this f now is my loss function, right? And we typically assume these loss functions to be L smooth. And that means that these loss functions are differentiable, so we can take gradients. That means that nonlinear activations are not allowed, so you have to make sure that they are soft somehow, like sigmoids. And when I talk about L smooth functions in general, we do not assume any convexity. So they are just standard smooth functions that are differentiable. And L smoothness also enforces that these functions cannot grow faster than a quadratic. So L smooth function basically are upper bounded by a quadratic function times a constant L at every point over the function. So basically that means that this function will always have kind of the growth factor, which behaves like a quadratic up to a certain multiplier. And if you recall, gradient descent step sizes are always proportional to 1 over L, right? So it means that if a function grows faster than an L-smooth function, L is infinite, it means that the gradient descent step size 1 over L0, right? So if you want to follow a gradient, the function shouldn't be worse behaved than an L-smooth function. So on top of it, we can add certain regularization. So convexity is 1. So if a function is convex and L-smooth, we know that, for example, a convex function is bounded below by its tangents. So that is the property we typically use in order to prove several results. And if a function is convex, we know that it has a unique minimum, but that minimum is not necessarily achieved at only one point. It could be a flat minimum, so several points, could achieve that minimum. So in contrast, we have strongly convex functions, and strongly convex functions are defined as functions that are bounded below by a quadratic. So when a function is bounded below everywhere by a quadratic, you know that this function cannot be flat. Actually, this function cannot be worse than x squared at any point, right? So the point at where this function achieves the minimum value is also unique. So unique minimum, unique minimizer, and in this case, just that it's well behaved, it's not going to have discontinuity, it's differentiable, etc. But much else is we cannot enforce here. So when I want to minimize functions, typically I said in the beginning that we are given first order information, so all we know are gradients. So minimization problem is equivalent to searching for a point where the gradient is 0, right? And this is what we call stationary points. So a point where gradient nabla of this function x star or this function f at x star. So this is a stationary point if this property holds its gradient is 0, right? And you can now go back to my earlier figure and notice that if it's a non-convex function, then this property does not tell me whether the point x star was a minimum or a maximum or a saddle point. If it was a convex function, we don't know that this x star that my algorithm has given me, is it the one unique x star, because that doesn't exist. All we know is that the function value of this x star is unique. And when we have strongly convex functions, this algorithm is returning a very good point because it's the unique minimizer of the function that I want to minimize, right? So we want to keep these aspects in mind when we go about building algorithms. So next up, how do we implement an algorithm that gives me a stationary point? And the intuition is very simple, right? So the intuition, think of a parabola, or think of a bowl, the soup bowl, right? And if you want to go to the bottom of the soup bowl, then you look at the direction where the soup bowl increases the most, and you take a step in the direction of that, away from that increase, right? So basically, it says that if you have some estimate of the minimizer of the function x old, and you move in the negative direction of the gradient at that point, then you will get a new x new. And what we know is that f of x new is less than or equal to f of x old. Okay. And this inequality is not strict, and it's strict only if the function was strongly convex. Okay. So formally, this is how the algorithm then looks like. So xk is my x old, and I'm going to move in the direction of the negative gradient, right, away from the steepest increase. And I want to scale this increase by alpha, because depending on how fast you increase, you want to take a smaller step. And then what you get in result is what is your x new. And we know that if your functions are L smooth, we have certain guarantees of how f of xk plus 1 relates with f of xk. And so if you think about gradient descent for different function classes now, we have these three results. So we know that for non-convex functions, gradient descent guarantees that the norm of the gradient goes to 0 at a certain rate, which is 1 over square root of k. Okay. And for convex function, gradient descent guarantees that the minimum value of the function and the minimum value at the iterate of the gradient at the iterate of gradient descent xk goes to 0 at 1 over k. And for smooth and strongly convex function, when you have a unique minimizer, we know that this distance goes to 0 exponentially. Okay. And another important thing to note here is the metric that we are using to prove convergence, right? So for non-convex functions, because at a stationary point, the function value at that stationary point is not necessarily unique because it has local minima. So we cannot seek this type of a metric for a convergence proof for function of minimization method for non-convex functions. The guarantees we have, the metrics we use are with respect to the norm of the gradient, and we ensure that the norm of the gradient goes to zero. Is kind of the best we can do. In convex functions, we cannot have a distance between xk and x star because x star is not necessarily unique, right? And when we have strongly convex functions, then both of these make sense because x star is unique, xk is your iterative gradient descent. So we can define such a metric. Okay. So just a quick detour. So gradient descent. So we know this is a first order method because it only looks at the first derivative or gradient of the loss function. Is this the fastest first order method? It's a question. Is it? It's not, right? Because you can speed it up by using momentum. So a very quick intuition is that functions that do not look like perfect parabolas or perfect bowls, which are steeper in one direction versus the other, right? In this case, if so this function is like Lx square plus mu y square in R2, where L is much higher than mu, right? So if you choose an arbitrary point in this function, the maximum growth is in this direction. So negative gradient will take you there, and you will see that it will zigzag a lot before coming to the minimizer. And one can improve the convergence by looking at a second order term, which is what we call momentum. So basically, if you take 2 points, x0 and x1, and you look at the error or the x1 minus x0 vector, which is in this direction, right? You see that my algorithm now takes a linear combination of my x1 minus x0 and the gradient red, right? So it kind of comes somewhere in the middle. So if you look at the trajectories of this algorithm, you see that in the first 25 steps, it goes much closer to the true minimizer versus gradient descent. And this is what, momentum is kind of, or first, or adding a pass iterate kind of buying us, right? Increases kind of like the oscillation where it comes much faster. And we know exactly, you can quantify this relationship. So for smooth and strongly convex functions, you remember the convergence is exponential. So natural log of 1 over epsilon is basically that exponential convergence. So if you want epsilon to be 10 to the power minus 6, then 1 over, this is 10 to the power 6. So this is natural log of 10 to the 6 times kappa. So for a given accuracy of epsilon, adding momentum is square root of k kappa faster than without momentum. And kappa is the difference between, the parabola or the steepness of the parabola in one direction versus the other, right? And if this were to be a strongly convex function like x square plus y square, where it's x square plus y square is just concentric circles, right? Perfect parabola, then momentum is not giving us much. But when you have functions that are kind of fast growing in one direction and narrow on the other, then momentum buys you a lot. Same results hold for convex functions and for non-convex functions. However, with one caveat that the proof of these rates or acceleration leading to faster convergence with respect to gradient descent can only be shown by Nesterov methods in general, and not by this type of momentum, which was done by Nesterov's PhD advisor, Polyak. And this is what we call heavy ball. So heavy ball proofs are not there, but Nesterov acceleration is proved analytically. Okay. So distributed optimization. So we want to take the machinery that I gave you and extend it to methods where data is now distributed over multiple machines. Okay. So let's try to rethink this problem. So this is a very simple setup, linear regression. I have a bunch of points in R2. I want to fit a straight line through them. And now what I'm going to do is I'm going to take these points and distribute them among multiple machines. So I have 4 machines here, and each machine has, a different number of points. So 4, 4, 4, 4, 4, 5, 5. So a total of 3 5s and 1 4. So total 19 points, right? 3 machines have 5, 5, 5, and 1 has 4. And you can see that if you only look at the magenta machine, right, the trend is good enough, right? It's still in the direction of the global trend, but if you look at the orange and green machines, they are saying that the trend is the positive slope, which is completely off the true distribution, right? And in this case, I have machines indexed by I. Each machine has a local data, which is indexed by J. And I am interested in finding 2 parameters, slope and intercept. So I basically, the data is given to me as 2 coordinates, X and Y. So I take the X coordinate and I predict what y is by using this equation. And then I subtract it with the true y, and I learn what slope and intercept is the best that minimizes this error, right? So if I implement gradient descent at each node on its own, then nothing is going to happen in terms of learning the global slope and intercept. So what I want for my distributed algorithm is that I want all nodes to agree, right? I want all nodes to agree on the slope and intercept, and I want that agreement to be on the optimal solution. There are two kind of ingredients that I want. So formally speaking, I can write the optimization problem as a global f, this uppercase f, which is the sum over local losses, right? And this local fi is a loss function at every node, every machine, that is just based upon their own data. And this data does not have to be the same size as other machines. The data could be vastly heterogeneous. For example, I have all images of cats and Raj has all images of dogs. And then these machines communicate with respect to some local network. The communication is not necessarily bidirectional, and the communication does not even have to be kind of on a static deterministic known graph. These graphs could be random according to certain assumptions that we can introduce. Okay. So the first method that was done, that was provided to solve this problem is what is known as mix and descend. So if you ignore the red part in this equation, this is a gradient descent done at each node. What the red part does is that it at node 1, for example, it looks at the neighbors of node 1 and so node 1 asks all of its neighbors to send node 1 their estimate of the slope and intercept. Then node 1 takes a linear combination of the slope and intercept, and then takes a direction in the step of the local loss function, the gradient of the local loss. So some regularity requirements that we need for this algorithm is that the weight matrix W is an averaging matrix, basically, right? So all elements are non-negative and they sum to 1. So it's a weighted average. And we want, if you look at the collection of all the weights, so what weights node 1 assigns to nodes 2, 3, and 4, and what node 2 assigns, node 3 assigns, node 4 assigns, it's going to be a 4 by 4 matrix. We want this 4 by 4 matrix. We need this 4 by 4 matrix to be doubly stochastic. Means that the row sums are 1, column sums are 1. And implementing a matrix in a distributed sense from the perspective of one node, when you have many nodes, implementing such weights is non-trivial. But there are simpler kind of ways to do this. And the convergence rate that this algorithm guarantees is that this is called distributed gradient descent DGD. The error converges linearly or exponential, right? But then it settles to a steady state, so it doesn't go to 0. In the paper, they showed exact convergence, but their alpha has to go to 0, the learning rate, which decreases the convergence rate, basically. So if you want to keep these algorithms converge faster, you want this alpha to be fixed. But if this alpha is fixed, then you cannot converge to 0. You will always have a steady state error. So this is how the convergence looks like. So distributed gradient descent versus gradient descent, they both come down linearly on a log scale, which is exponential on the ordinary scale. And then gradient descent goes to 0 because it has access to all data. But in the local sense, each node, they will not converge to 0 error, and every node converges to a steady state error. Okay, any questions so far? Move on.
So just to highlight things, the idea is still that the data is local. So
data is local.
I could argue that the data could be evenly distributed across the servers, but here you're assuming that the data is very local, and therefore that causes this.
Yeah. So if you think of your data set and you uniformly distribute this data set to individual machines, then you can assume that the distribution of the data at each machine is going to be very similar to the global distribution. Right. In which case you will still incur a non-zero steady state error, but this will be much closer to the much lower. Yeah. But in a scenario where the data was biased, and in my linear regression example, you can see that data was biased, right? So the orange nodes, it was not a representation of the truth, right? And which is the case when I have certain pictures of a certain image class, and you have a different image class, you have a different image class, right? So data distribution heterogeneous versus homogeneous is kind of a an ingredient that one has to consider as well.
Yes.
Okay, so how do we remove the steady state error? And this is where our work kind of kicks in. And this is what we do with the help of what we call gradient tracking. But before we go into the actual algorithm, I'll quickly describe the cause of the error, right? So first consider that or note that the global loss function, which is the sum over all loss function, right? The x star, the stationary point I'm seeking, has the property that the gradient of the global loss function is 0 at x star, right? So if you look at what distributed gradient descent DGD does, if I give DGD x star, right, then so this is the algorithm in gray, and imagine that every node knew what x star was, for example, right? So one property you want for these algorithm is for x star to be a fixed point of this iteration. So since these weights sum to 1, and this x star doesn't depend on the weight, this is 1 times x star. But remember that local loss function evaluated at x star, which is the global minimizer, will not be 0 gradient, right? Because this is the global optimizer is not the best case for your local data. And this is the error, right? So if the local loss is closer to the global loss, this quantities will be very close to 0. Not exactly 0 unless the data was replicated across certain machines, right? So we know that because the global optimizer is optimal for the global loss, then local loss will not be 0, it won't be a stationary point. We'll XR will not be optimal. And in order to remove this problem, what we could do is that instead of using a local loss function here, I'll replace it by another variable, which is an estimator of the global loss. And this is how the algorithm looks like. So this is the original DGD, but instead of using gradient, right, I'm going to use a different variable which has another dynamics, and I can show that this auxiliary dynamics, this auxiliary variable, tracks the global gradient as k goes to 0. So you can see that in the limit k, yk will be the global loss function, in which case the problem that I showed earlier does not exist. Okay. So the steps to make all of this work are a bit more involved, and we have papers that I can point towards. But this is the basic idea, right? So the requirement of this algorithm is that the weights that you collect on the top equations, if you collect them in a matrix, it's row stochastic, so all rows sum to 1. And for the gradient tracker, all columns sum to 1. And we also were able to relax this requirement of doubly stochasticity on the weight matrix, which requires both rows and columns sum to 1, right? So now we only know row stochastic and column stochastic. These weights are a little easier to design in certain communication protocols.
Sure.
Yeah.
So why do you call it stochastic? Because you say it has to sum up to 1. So what is the stochastic part then?
So the stochastic is in the context of Markov chains, right? Where we say that a matrix of transition probabilities is stochastic if the row sum is 1. So it's not random stochastic. It's just stochastic here means that they sum to 1. So it's a matrix of probabilities.
I was not familiar with the term.
Yeah. And row stochasticity basically means that all the incoming weights sum to 1, and column stochasticity means that all the outgoing weights sum to 1. So in a Markov chain sense, this is the incoming probabilities of transition to your node versus the outgoing probability. Okay. And then we were able to show that certain other algorithms that were known in the literature, some of them introduced by our group, some by some other groups, they were actually a special case of this umbrella algorithm. So that was a kind of a cool result. And next, we were able to also add momentum to the distributed variant, right? So momentum means that you add a second order type of a term here. And there are several variants of this type of a scheme. This is a heavy ball or polyx style momentum. You can also do Nesterov style momentum, and you can claim certain convergence guarantees, etc. And if you are interested, we can go into detail. And lastly, we were also able to use this framework and extend it to mobile nodes. So what happens now is that all of these weights, I've marked them red, right? So these weights are a function of time. And if you collect the weight matrix at time k of these incoming weights, right, then we assume that this time k incoming weight matrix is row stochastic, but if you look at the next time, k plus 1, the zeros and non-zeros are not necessarily the same zeros and non-zeros before. And if you look at any snapshot of this weight matrix, then this snapshot is also not irreducible or means that it come from a strongly connected graph. So means that you could have at time k nodes kind of sparsely distributed, and they talk to a few neighbors, but the network is not connected. It's kind of disconnected, right? And the network does not have to be connected for every time k. So what we were able to show, and there are some variations of this result as well, that we were able to show what we call C bounded strong connectivity. So means that if you look at the graph at time k, and you look at the next C graphs, right, or networks, and you take the union of all these C graphs, then that union is strongly connected. And this is true for every k. So I know it's a bit of a stronger assumption, but basically, if you think about it, if your robots are in a room, right, and they are in a confined setting, then it's saying that each robot is able to see enough over a certain finite period of time. Means that you're not allowing the robots to drift apart from each other and then go in infinity forever, right? They have to kind of come back. So this is kind of an information mixing requirement, which makes sure that your network kind of becomes whole over a certain time step. And there are extensions to these results where you can assume not that the graph is not connected every C kind of snapshots connected as a mean graph, and you can do those as well. So there's a lot of follow-up work on this idea, which we call gradient tracking. This will get descent with gradient tracking. The mean graph work was done by Shipu, who is also our collaborator. We have a few papers together. Our collaborators at my colleague at in Cyprus, Apostos, Ricos, and Themis Toklis, they worked on communication imperfections and quantization, etc. Right? We have a lot of other variations over the years. If you're looking for something to improve, then I can give you one idea. So remember, gradient descent for smooth and strongly convex functions have a dependence of kappa, right? So I showed you kappa natural log 1 over epsilon. If you recall, heavy ball or Nesterov is square root of kappa, right? So the maximum we can push this boundary with respect to the condition number of the smooth strongly convex function is square root of kappa. And the AB method that I showed you for directed graphs, the result is kappa squared. And for undirected graphs is kappa 5 over 4. So this is AB undirected. It's still larger than kappa, right? It's 1.1 to 1.25, right? So we still have some boundary to push. And for directed graphs, we have kappa squared. So we have not reached there. But we also believe, between me and my students, that these constants or these exponents are a shortcoming of the analysis, not the algorithm. So we feel that some of the assumptions we have made in order to prove convergence, they kind of lead to these type of higher exponents, but we believe that there is a way to prove it. And if I remember correctly, there was some paper on primal dual methods that hinted kappa for AB type methods, but I haven't looked too closely at that. Then if you want to add momentum, for directed graphs, adding momentum to AB style methods, the convergence is still open. So there is no formal convergence proof that proves that AB algorithm over directed graphs with acceleration will be faster than AB without momentum for directed graphs. For undirected graphs, there is a method done by Nali and her student at Harvard, which shows the exponent to be 5 over 7. So remember that the best case exponent here is 1 over 2. Right? So I believe that you could still come up with some variation, some trick of adding momentum to a distributed gradient descent type algorithm that gives you something between 1 over 2 and 5 over 7. And this is from several years ago. So maybe they have pushed the envelope, but I don't think there's a new result in this context. Okay. And this is the convergence plot. So recall the magenta and black are from my previous figures. So I said that gradient descent goes to 0 exponentially, so linearly on a log scale. Distributed gradient descent converges linearly, but to a steady state error. And then the AB method, because it does gradient tracking, it's able to resolve or remove the steady state error. So that's the blue dashed line. And then when we add momentum to AB, we get to this blue curve experimentally. We haven't proved it. So we know that this curve will go to 0 exponentially, but we cannot prove that this will be faster than without the momentum, which is the blue dash. So that's the acceleration that needs to be proved. And the red part is adding acceleration to gradient descent, the centralized one, which is much faster. And of course, that's like the lower bound in this context. And what happens when we don't know the gradients perfectly, right? Which means that the local gradients are not true gradients, but only known through up to a certain error. Everything kind of breaks. So in this simulation, I'm assuming that the gradient of the local loss function that I'm plugging in into gradient descent is not a full gradient, like it's a stochastic gradient type of problem where these gradients are sampled with or added finite variance noise. And in this case, you can see that things that look quite nice before, they just are not as nice. And we have an analytical characterization of this result by some other researchers. And they show that the average error, right, between the iterate at time k and node I of distributed stochastic gradient descent as time goes to infinity will be a function of these three terms. So nu square is my variance. So if k goes to infinity, you still settle on something like this, which is non-zero if your variance is non-zero, right? So if your variance is not zero, the first two terms go away, but you still have a non-zero term, which is eta. It's dependent on eta, and eta quantifies the difference between your loss function versus the global loss function. So this is distributed stochastic gradient descent. Gradient tracking is not there. So what gradient tracking does that, first of all, for non-stochastic problems, variance is zero, so first two terms are not there. But gradient tracking eliminates this issue because you're not taking a step in this direction. You are taking a step in the direction which is asymptotically the same as the global gradient, right? Okay, so the next part of this work that we did is we tried to remove this dependence on nu square as well. So eta we can remove by gradient tracking. Now we'll try to remove the dependence on nu square. And this is what we call, the GT plus VR framework. We have a few different variations of it, but I'll give you one flavor and we can talk about more, or I can point you in the right literature. Okay, so remember this was my problem setup, right? So each node had its own data set. So given one point, any one point, this is the loss function. And then you sum it over all your data, so all magentas, and then sum over all machines. And in another scenario, you can basically, every node had its own data set, right? And I need to compute a gradient over my entire data set, right? So what stochastic optimization algorithms do, or mini batching does, they pick a mini batch of your own data set. Suppose if I have 100,000 images of, whatever, cats, cows, or dogs, I will sample a mini batch. Mini batch size could be, 10, 20, or just one, right? And instead of computing the full batch gradient, I'll compute a batch gradient over a mini batch, right? My local gradient over this mini batch. So what I implement is basically Fi, where the second index tau k is different for every step of the algorithm, and tau k is stochastically chosen batch from my own, right? And you can see that this is a surrogate for my full local gradient, and this surrogate is an estimate of my local gradient, or is like a noisy version of the local gradient, right? And this is what adds to adds stochasticity to my underlying algorithm. So my local loss function, evaluated at just one, let's say for the sake of argument, randomly chosen data point, is far away from my local full batch, my own full batch, which is far away from the global. And this distance we were able to reduce using gradient descent. This distance we can reduce using another method that takes the samples and tries to estimate the entire batch. Okay, and this is what we call variance reduction. So this was done in centralized machine learning, and they use variance reduction methods. Like, so if you recall, there are some stochastic gradient methods that that keep an estimate of the gradient as they evolve. And the idea is that the variance of that estimate as gradient descent evolves goes to 0. So it's the same idea. So we were able to use some variance reduction methods that arbitrarily samples from your local loss, gradient of the local loss, right? Pass it through an estimator, gets an estimate VI of the local loss, the gradient local loss, right? And then we mix local loss or the estimate over the network. So we have several variations, as I said, of these estimators or these network level fusions. And all of them, when we combine, it gives us a family of algorithms that we call GT plus VR. So VR is the appropriate variance reduction method that you use. GT is the gradient tracking method that we use in order to fuse information over the network. And you can also throw in variance with respect to, some where the graphs were random or there was latency or there was quantization, etc. And the overall scheme basically converges to the true X star, right? This is one such algorithm, GT SARA. So this is gradient tracking. This is the one I showed you before. SARA is a centralized variance reduction method that was proposed a few years ago. So we combine the two methods, but combining is non-trivial. So when you plug and play this in a distributed setting, the proofs are not easy because then all of these estimators are locally propagated within the network. So the network kind of comes into play, and if the network is too weak, then convergence kind of deteriorates. So in one such setup, I can show you the paper. We were able to show some exciting results. So in this case, now I have expanded the problem from smooth and strongly convex to smooth and non-convex. So if you look at the title, each loss function, local loss function over individual data is a non-convex function, right? And I am assuming for the sake of simplicity that each node has the same number of data points, M. So I have total of N machines, and every machine has little m data points, right? They don't have to be, but for the sake of the result. So what we can show is that, so we look at the first equation, right? And recall the metric. So it's a non-convex function. So all we can show that the gradient, the norm of the gradient goes to 0 at each node I with probability 1, right? So we can show this in an almost sure sense and also in the mean squared sense. And if you want to pose a different question, that how many gradient computations are required to reach an epsilon accurate solution, right? So every node is computing several gradients. So what is the total number of gradients you need to compute if you want the solution to be close to, or you want the loss function, right? Whatever was my metric here, if you want this loss function to be less than epsilon, right? And we have a kind of a complicated bound. So H is the total number of computations needed. But we can simplify it. The full result is in the paper. This paper is, if I remember correctly, in SIAM Journal on Optimization. But in a certain regime, you can relax, you can simplify this bound. And this is the regime I give here. So basically, it's saying that if the number of machines and the number of data points per machine satisfy a certain equation, then the number of gradient computations you need satisfy the red equation, right? So before I explain the bound, I want to explain the result itself. So the number of computations that you require, n is n times m. So for us, what is the problem for a central machine, right? A central machine is given little n times little m data points, right? It's a stochastic non-convex problem because loss function at each data point is non-convex, and the machine samples from the total batch, so it becomes a stochastic problem. Then for the centralized machine, what is the number of gradient computations required to achieve epsilon solution, right? Epsilon accurate solution. This is the same number of computations that a central machine will require that is also met by our distributed algorithm, right, GT SARA, when n and m have a certain relationship. And we call this the big data regime. So in order to explain this, let me recall. So lambda, is lambda, right, not gamma?
Okay.
Lambda. So lambda goes to 1 if the network is bad, right? So means that if lambda goes to 1 for weakly connected networks, then this is not as bad as if it goes to, yeah, right? So if lambda goes to 1, this is 1 minus lambda is going to be a very small number. And this very small number is going to be much smaller because of the power 6. So in order to make this equation match, m has to be much larger, right? So this is what the result says, and this is why we call it the big data regime, right? So if you're given, so lambda is bad when the network is weakly connected, or it's like a line graph and you have many nodes, right? In which case, every node should have a lot of local data points for this bound to make sense, right? So, and as I said before, it's not that you take the gradient tracking method, which is designed for networks, and variance reduction method, which was designed for one node, and just slap them together and things work, right? Because somewhere the communication that I kind of pointed out earlier has to come in, and this is where the communication comes in. So if the nodes that you have kind of packed together to do this distributed computation do not communicate well among each other, then you cannot guarantee this rate. Like, so your distributed algorithm will still work, but the number of gradient computations will not match the centralized. So the algorithm is not going to be the optimal, right? So this is interesting because we are able to identify a regime where my distribution of the data per node, recovers the optimal rate, which you will do with centralized, but in a much more efficient, parallelized kind of a setting, right? So for a distributed algorithm to match the performance of a centralized algorithm, that's like, the holy grail, or like that's the thing that we aim for. But you can see that in a distributed sense, it's not going to be true for all scenarios. It's going to be true for a certain limited kind of a, data versus machine scenario. So matching this bound for any algorithm is critical, but under what conditions you match this bound is kind of like, where one can improve. So we believe that you could improve this exponent, right? You can decrease it from 6 to 2, which is going to be nice. But this is what I think one of the strongest kind of claims we have so far. I'm not sure if there is other work which improves on this type of a factor, but I'm sure we can find. So this concludes, the overall kind of, broad things that I wanted to talk about with respect to machine learning, training data, distributed paradigms, etc. One thing to note again is that in the context of autonomous agents, this lambda is not going to be fixed. So we will have, right? So if your graph is not fixed static graph, then this lambda is not going to be a fixed static constant. So how these bounds change is an open problem which we haven't studied. But yeah, I can show you one quick set of results. So this is where what we are doing is fine tuning the vision transformer model by Google. So vision transformer is trained over 14.2 million images, and there are roughly 21,000 classes, right? And there is another data set. I think the second one is maybe proprietary Google something. So trained over a very large data set, I think 300 plus 14, so maybe 314 million or something. The model architecture is given by this, transformer-based architecture. And the base model has 86 million parameters across, several layers of attention and stuff. So people have, so for a fine tuning or distillation or, some version of extension to these models is that you take the base model, which is already trained, and you give it a new problem, and you see how well it does on the new problem, right? So for example, the new problem could be CFAR 100, where your images come from 100 classes. And so you take the output head, instead of predicting 21,000 probabilities, you predict 100, and you see how good the model does, right? So zero-shot learning would mean that you just slap a new output head and you see what the model performance is. And then few shot learning is that you just retrain it on a few different examples. What fine tuning does is that you take the new data set, which is CFAR 100, you change some layers of this model, and then you retrain only those layers. You keep the rest of the model fixed. Am I making sense, right? So you could do fine tuning on CFAR 100. So fine tuning on CFAR 100 dataset would mean that I don't remember exactly however many CFAR 100 images are there, but you take some for training and you retrain a part of the model. And in our case, we have updated the model we only update the model parameters of the last block. So we keep the first almost, so it's an 86 million parameter model. So we keep almost 85 to 90% of the model fixed. We just look at the last model and retrain those 7 million parameters, and we do it in a distributed way. And we use stochastic minimatch AB for this fine tuning. And these are some numbers which are not that critical. I can just show you some visuals. So what I'm showing here is that I am displaying the attention mask that is learned by the model at the last possible layer. And this is the original image. So this is from the flowers data set. This is from animals or dog or something, cat and another flower. And this is the attention mask that the model learns, right? So basically where to pay attention in order to declare whether it was a flower of type A versus a flower of type B or something. So these are what the centralized mask looks like. And if I go this now on local data set, so this is centralized, and this is the result of local fine tuning where you don't see any other data. And you can see that on unseen classes at a given node, the attention mass that is learned by the local model is pretty much all over the place, right? These are on classes included in local data set. So basically, the top figure is saying if the model has seen cats before or dogs before, it will be able to find the right attention to put on the dog, right? But on a class that it has not seen before, like this cat, it won't be able to put the right attention mask. And this is the local one, right? So we expect that the distributed will do better, right? And this is the distributed attention mask at the end. So you can see that on unseen classes, the distributed vision transformer fine tuning was able to recover the cat, not exactly as a centralized, but close enough, right? Or yeah. Yeah, so I think with this slide, I'll conclude my talk. So basically, we talked about training very large models. And training very large models require distributing the computation efficiently and distributing the data efficiently. And in the realms of how do you want to distribute data versus how many machines do you have versus what type of network you have, right? We looked at a few different variations of the algorithms given by gradient tracking, which tries to fuse the gradients over the network, and variance reduction, which tries to kind of estimate the full local batch at each node, and combinations of them and different kind of extensions around those. So I'm happy to take questions at this point. This concludes my talk.